Okay, time again for another action-packed video presentation. Today's topic is Hooke's Law, and Hooke's Law was invented by Robert Hooke. And there's a picture of the gentleman. His time frame was 1635 to 1703 apparently, and a contemporary of Isaac Newton's. So Galileo opened the door to experimentation of physical phenomenon, and people started looking at all kinds of different things. Hooke did a few different significant discoveries, but what we're talking about today is what he discovered with springs and things. Of course, when we go through these things, all of our topics, we should be thinking about the implications outside of the physics classroom. So we'd like you to understand that part of what happened with the springs is that we were able to measure forces, because there's a predictability around force and the distance that a spring will stretch or compress, actually, be brought together. And you know this already from the spring scales that we've been using in class. So here's some questions we could be asking. How can you measure a force? How can you come up with that number? What type of forces could you measure? And what else can we do once we know what the forces are? What other kind of predictions can we make? So let's try to think of the implications outside of the physics classroom. Okay, so here's a little bit of vocabulary to get us going for Hooke's Law. Elasticity, like a spring, is something that you can compress or expand, and when you're done compressing or expanding it, it'll go back to its original shape, its original position. So that's what elasticity is about, that it'll go back to its original shape. And springs will do that. Can you think of something else that might do that? I'll give you a hint. It's a rubber band, but you might have thought about that too. Okay, so elongation is going to be how far something stretches. That's going to be the elongation, and we're going to be determining elongations for springs in this section here. Okay, another thing is the elastic limit, and you probably know that about a spring. Like if we stretched it too far, it will not go back to its original position. And you may have had the experience of owning a slinky at some time in your life. And a slinky is nice when you first get it. It stretches out, goes right back into the box. But then if you play with it a little bit too much, and if your little sister takes your slinky and starts playing with it, and it gets wrapped around the dog, and the dog falls down the stairs, and a lamp gets knocked over, and everybody's upset, the slinky will never go back to its original position. Yeah, that actually did happen to me. I thought I was over it. You'd think I would be. It was almost 50 years ago. But there you go, elastic limit. Once you go past that point, you're not going to get the slinky back in the box. Okay, let's see here. All right, so Hooke's law, in fancy terms here, says that the bigger the force, the longer the stretching is going to be. That should make some sense. But also that it's directly proportional. If I double the force, I'm going to double the stretching distance. So if I apply a force and I stretch this distance, if I double the force, I'm going to double the stretching distance. And that's what Hooke discovered, and that's why we call this Hooke's law. Okay, so here is Hooke's law in equation form, where F is the force applied to the spring, and X is going to be the elongation or the compression. For us, it'll always be the elongation, the stretching distance. And K is a spring constant. That depends on the spring itself. It should make some sense. Some springs are going to be harder to stretch than others. Some are going to be easy to stretch. And that spring constant will give you an idea of what will happen for a particular spring. So let's see how it works here. You got a problem in front of us. And of course, the first step is to identify the information. If you're stretched 10 meters, that's your X. The force is 20 newtons, and we want to know the spring constant. So we are looking for the K in the equation. There's our setup, and that turns out to be 20 divided by 10 is K. And the units here will be newtons divided by meters. So that's the idea for one of these basic problems. Well, this is time to start thinking of some questions here. How could knowing a spring's constant be useful? Well, why don't you think about that, and we can talk about it back in class again. How could this be useful? And then we'll add that to your notes a little bit later. Okay, so here we go. Here's another problem for us. Proportionality constant is another way of saying spring constant. So I'll introduce that term as well. Once again, we'll identify the information. There's my proportionality constant, and there's my stretching distance, and I am looking for the force. Force is K times X. So for this case, there it is, falling into place. The force will be 6 newtons. So hopefully this is making some sense to you. All right, let's take it a little bit further here, and we got to just complicate it just a little bit for Hooke's law. It doesn't get much, this is about as complicated as it becomes. But here I am giving you a mass, and we're hanging it from a spring. So if we are hanging a mass from a spring, and the constant is 200 newtons per meter, and the mass is 5 kilograms, what is the elongation? Well, it might surprise you to find out that the answer is 0.25 meters, but let's take a look at why. Okay, because if you are hanging a mass from a spring, well, the force pulling it down would be the weight. And remember again that weight is mass multiplied by acceleration due to gravity. So here the force is the weight, and that is 49 newtons. People confuse weight and mass oftentimes. That's why we did that weight-mass activity. But here I hope you can see that the force pulling down on the spring would be 49 newtons. Now we're ready to solve the problem. Here's our information. We've now got the correct force, we've got the spring constant, and here's our solution. F is equal to kx. So by plugging in the numbers and dividing off the 200 from both sides to get x by itself, we get our answer of 0.25 meters. Well, that's about it for that problem, and that's about it for this presentation. If you have any questions, please ask them back in class. Look forward to seeing you there.